Okay, for 6.1 day 2, we're going to look at solving differential equations. And to solve a differential equation, we're going to break it down into these 3 steps right here. Step 1, we're going to separate all our variables. So for most of the time, that's going to be y's and x's. So we want our y's, dy's on one side, x's, dx's on the other. After we have our variables separated, we're going to go ahead and integrate what we have, and then we're going to solve for c. After we know what c is, we're going to resolve the equation for y, and then we're going to call it a day. With these, since you are solving, we need to make sure they're in check that the given points in our solution work out, especially if the equation includes a square root or any even root for that matter, because we cannot take the even roots of negative numbers. So jumping right into these examples, example 6, we're going to follow our steps. They go ahead and give me the differential equation. And then they give us the initial condition that y of negative 1 equals 1. So starting our process, we're going to go ahead and separate our x's and y's. I went ahead and moved the y squared to the left by dividing, dx to the right by multiplying it up. After you have your y's and x's separated, we go ahead and take the antiderivative. Antiderivative for my left-hand side is going to be negative y to the negative 1. And then the antiderivative of 1 plus 2x is going to leave me with x plus x squared plus c. Now that we've taken the antiderivative, we're going to go ahead and plug in our initial condition and solve for c. Doing so is going to get me to find out that c equals negative 1. From there, after you have c, we can go ahead and plug back into our differential equation. After the one we've integrated, I'm going to go ahead and plug in c. And then now to finish it up, we need to solve for y. So I'm going to do so by dividing everything by negative 1. And then from there, the easiest way to get rid of this negative 1 exponent is to go ahead and raise the other side to the negative 1 power. Give me y equals negative x minus x squared plus 1, and that whole quantity is being raised to the negative 1 power. So that problem right there is just a basic differential equation. We're going to step it up in difficulty in these next few problems. So next one. I want to solve the differential equation dy over dx equals 2x over y. Same first step, separate x's and y's. Have my y's on my left. Go ahead and take the antiderivative. It's going to give me y squared over 2 equals x squared plus c. We have an initial condition again, so I'm going to go ahead and substitute in for x and y. And then go ahead and solve for c. Get c to equal negative 1/2. From there, go ahead and plug in c for the equation where we took the antiderivative. Gives me y squared over 2 equals x squared minus 1/2. And then given that f of 1 equals negative 1, we're going to go ahead and solve this. So multiply every single thing by 2. Lastly, we got a square root. So we end up with y equals the square root of 2x squared minus 1. I remember that we need to go ahead and check, especially because we have an even root. So checking our answer, if I plug in the initial condition, f of 1 equals negative 1, we're going to get negative 1 equals a positive 1. Since I need to be negative 1, and when we solve square roots, we can have a plus or minus out front, I'm going to go ahead and throw the negative in front of the square root. Doing so allows us to have negative 1 equals negative 1. So our solution here would be y equals negative square root 2x squared minus 1. All right, before we go into our last couple examples, we need to do some quick review with exponents. So properties of exponents, when you're multiplying powers that have the same base, you can go ahead and add the exponents together. So 8a is going to turn into e to the x plus 2. For b, same deal. Multiplying, same base. Exponents, you go ahead and add them. And then last one, c. When I'm going from log form to exponential, you're going to go ahead and take the base. So natural log is a base e. And then raise it to the exponents on the other side. Leaving with y equals e squared. Big thing you need to realize is that e raised to any number, whether it be a constant or in this case, the 2, realize that that whole thing, that whole power is a constant because e is a number. All right, we're going to look at solving differential equations in the form of dy over dt equals ky. So we have a constant times y. We're going to follow many of the same steps to do so. So example 9, step 1, I want my y's on the left, everything else to the right. So I got dy over y equals k dt. Go ahead and take the antiderivative of each side. Antiderivative of 1 over y is just going to be the natural log of y. And that's because, think about this, if I were to rewrite it y to the negative 1 and take the antiderivative, we can't divide by 0. So since we have an issue there, it just turns into the natural log of y. Right-hand side, antiderivative of k dt is going to be kt, and I got a plus c on the end. At this point, I'm going to go ahead and switch forms to make it y equals. Since I have base e, I'm going to go ahead and raise e to everything that's on the right-hand side. That's my exponent. So e to the kt plus c equals y. We're going to do properties of exponents, but backwards. Doing it backwards, we can break this down to e to the kt times e to the c. E to the c is a constant, so I'm going to go ahead and circle that, and I'm actually going to call it a super constant. We're going to let that be capital A. So whenever I have e raised to a constant, we're going to go ahead and let that be capital A, signifying as a super constant. Go ahead and rewrite my answer. I got y equals a e to the kt. And since I didn't have any initial conditions, we're done. All right, last example for this video. Putting it all together. We have an initial condition, f of 0 equals 4. Solve the differential equation. So I went ahead and moved my y's to the left, x's to the right. Antiderivative, since my denominator has y in the first degree, my antiderivative is going to be natural log of the denominator. So natural log, absolute value y minus 2, equals, right-hand side is going to be x to the 4 over 4 plus c. At this point, since I have a natural log, I'm going to go ahead and switch forms. Switching forms is going to leave me with y minus 2 equals e to this whole right side as my exponent. Properties of exponents allows me to rewrite it as y minus 2 equals e to the x to the 4 over 4 times e to the c. Like we did on the previous one, this e to the c is going to be a super constant for us. So I'm going to go ahead and let it be a. And then I solve for y. For this problem, since we have an initial condition, we can go ahead and figure out what our super constant is. So I have an x value of 0, y value of 4. We go ahead and plug everything in. I'm going to get 4 equals a e to the 0 to the 4 power divided by 4 plus 2. Remember, e, or anything to the 0 power, is going to be 1. So I have 4 equals a plus 2. And solving for a, I get a value of 2. Go ahead and substitute back in. We're going to have a differential equation with the answer y equals 2 e to the x to the 4 over 4 plus 2. Last thing, which isn't going to pop up in tonight's homework, but will in the future, the domain of solution. Domain of solution to a differential equation is going to be the largest continuous interval of x on which the solution curve exists through that given point. We're going to go ahead and take a look at that in warm-ups and examples in the next couple of classes.